Implementation of Replication Logs. How does leader-based replication work under the hood? Several different replication methods are used in practice, so let's look at each one briefly. In the simplest case, the leader logs every write request statement that it executes and sends that statement log to its followers. For a relational database, this means that every insert, update, or delete statement is forwarded to followers, and each follower parses and executes that SQL statement as if it had been received from a client. Although this may sound reasonable, there are various ways in which this approach to replication can break down. Any statement that calls a non-deterministic function, such as now to get the current date and time or ran to get a random number, is likely to generate a different value on each replica. If statements use an auto-incrementing column, or if they depend on the existing data in the database, e.g., update where some condition, they must be executed in exactly the same order on each replica, or else they may have a different effect. This can be limiting when there are multiple concurrently executing transactions. Statements that have side effects, for example triggers, stored procedures, user-defined functions, may result in different side effects occurring on each replica unless the side effects are absolutely deterministic. It is possible to work around those issues. For example, the leader can replace any non-deterministic function calls with a fixed return value when the statement is logged so that the followers all get the same value. However, because there are so many edge cases, other replication methods are now generally preferred. Statement-based replication was used in MySQL before version 5.1. It is still sometimes used today, as it is quite compact. But by default MySQL now switches to row-based replication, discussed shortly if there is any non-determinism in a statement. VaultDB uses statement-based replication and makes it safe by requiring transactions to be deterministic. In Chapter 3 we discussed how storage engines represent data on disk, and we found that usually every write is appended to a log. In the case of a log-structured storage engine, CSS tables and LSM trees on page 76. This log is the main place for storage. Log segments are compacted and garbage collected in the background. In the case of a B tree, see B trees on page 79, which overwrites individual disk blocks. Every modification is first written to a write-ahead log so that the index can be restored to a consistent state after a crash. In either case, the log is an append-only sequence of bytes containing all writes to the database. We can use the exact same log to build a replica on another node. Besides writing the log to disk, the leader also sends it across the network to its followers. When the follower processes this log, it builds a copy of the exact same data structures as found on the leader. This method of replication is used in PostgreSQL and Oracle, among others. The main disadvantage is that the log describes the data on a very low level. A WAL contains details of which bytes were changed in which disk blocks. This makes replication closely coupled to the storage engine. If the database changes its storage format from one version to another, it is typically not possible to run different versions of the database software on the leader and the followers. That may seem like a minor implementation detail, but it can have a big operational impact. If the replication protocol allows the follower to use a newer software version than the leader, you can perform a zero downtime upgrade of the database software by first upgrading the followers and then performing a failover to make one of the upgraded nodes the new leader. If the replication protocol does not allow this version mismatch, as is often the case with WAL shipping, such upgrades require downtime. An alternative is to use different log formats for replication and for the storage engine, which allows the replication log to be decoupled from the storage engine internals. This kind of replication log is called a logical log, to distinguish it from the storage engine's physical data representation. A logical log for a relational database is usually a sequence of records describing writes to database tables at the granularity of a row. For an inserted row, the log contains the new values of all columns. For a deleted row, the log contains enough information to uniquely identify the row that was deleted. Typically this would be the primary key, but if there is no primary key on the table, the old values of all columns need to be logged. For an updated row, the log contains enough information to uniquely identify the updated row and the new values of all columns, or at least the new values of all columns that changed. A transaction that modifies several rows generates several such log records, followed by a record indicating that the transaction was committed. MySQL's bin log, when configured to use row-based replication, uses this approach. Since a logical log is decoupled from the storage engine internals, it can more easily be kept backward compatible. allowing the leader and the follower to run different versions of the database software, or even different storage engines. A logical log format is also easier for external applications to parse. This aspect is useful if you want to send the contents of a database to an external system, such as a data warehouse for offline analysis, or for building custom indexes and caches. This technique is called change data capture, and we will return to it in Chapter 11. The replication approaches described so far are implemented by the database system without involving any application code. In many cases, that's what you want, but there are some circumstances where more flexibility is needed. For example, if you want to only replicate a subset of the data, or want to replicate from one kind of database to another, or if you need conflict resolution logic, see handling write conflicts on page 171. Then you may need to move replication up to the application layer. Some tools, such as Oracle Golden Gate, can make data changes available to an application by reading the database log. An alternative is to use features that are available in many relational databases, triggers and stored procedures. A trigger lets you register custom application code that is automatically executed when a data change write transaction occurs in a database system. The trigger has the opportunity to log this change into a separate table from which it can be read by an external process. That external process can then apply any necessary application logic and replicate the data change to another system. Database for Oracle and Bucardo for Postgres work like this. For example, trigger-based replication typically has greater overheads than other replication methods and is more prone to bugs and limitations than the database's built-in replication. However, it can nevertheless be useful due to its flexibility. Problems with replication lag. Being able to tolerate node failures is just one reason for wanting replication. As mentioned in the introduction to Part Roman 2, other reasons are scalability, processing more requests than a single machine can handle, and latency, placing replicas geographically closer to users. Leader-based replication requires all writes to go through a single node, but read-only queries can go to any replica. For workloads that consist of mostly reads and only a small percentage of writes, a common pattern on the web, there is an attractive option: create many followers and distribute the read requests across those followers. This removes load from the leader and allows read requests to be served by nearby replicas. In this read scaling architecture, you can increase the capacity for serving read-only requests simply by adding more followers. However, this approach only realistically works with asynchronous replication. If you try to synchronously replicate to all followers, a single node failure or network outage would make the entire system Roman 3. The term eventual consistency was coined by Douglas Terry et al., popularized by Werner Vogels, and became the battle cry of many NoSQL projects. However, not only NoSQL databases are eventually consistent, followers in an asynchronously replicated relational database have the same characteristics unavailable for writing. And the more nodes you have, the likelier it is that one will be down, so a fully synchronous configuration would be very unreliable. Unfortunately, if an application reads from an asynchronous follower, it may see outdated information if the follower has fallen behind. This leads to apparent inconsistencies in the database. If you run the same query on the leader and a follower at the same time, you may get different results, because not all writes have been reflected in the follower. This inconsistency is just a temporary state. If you stop writing to the database and wait a while, the followers will eventually catch up and become consistent with the leader. For that reason, this effect is known as eventual consistency. Roman 3. The term eventually is deliberately vague. In general, there is no limit to how far a replica can fall behind. In normal operation, the delay between a write happening on the leader and being reflected on a follower, the replication lag, may be only a fraction of a second, and not noticeable in practice. However, if the system is operating near capacity or if there is a problem in the network, the lag can easily increase to several seconds or even minutes. When the lag is so large, the inconsistencies it introduces are not just a theoretical issue but a real problem for applications. In this section we will highlight 3 examples of problems that are likely to occur when there is replication lag and outline some approaches to solving them. Reading your own writes. Many applications let the user submit some data and then view what they have submitted. This might be a record in a customer database, or a comment on a discussion thread, or something else of that sort. When new data is submitted, it must be sent to the leader, but when the user views the data, it can be read from a follower. This is especially appropriate if data is frequently viewed but only occasionally written. With asynchronous replication, there is a problem, illustrated in Figure 5-3. If the user views the data shortly after making a write, the new data may not yet have reached the replica. To the user, it looks as though the data they submitted was lost, so they will be understandably unhappy. Figure 5-3. A user makes a write, followed by a read from a stale replica. To prevent this anomaly, we need read-after-write consistency. In this situation, we need read-after-write consistency, also known as read-your-writes consistency. This is a guarantee that if the user reloads the page, they will always see any updates they submitted themselves. It makes no promises about other users. Other users' updates may not be visible until some later time. However, it reassures the user that their own input has been saved correctly. How can we implement read-after-write consistency in a system with leader-based replication? There are various possible techniques. To mention a few, when reading something that the user may have modified, read it from the leader. Otherwise, read it from a follower. This requires that you have some way of knowing whether something might have been modified, without actually querying it. For example, user profile information on a social network is normally only editable by the owner of the profile, not by anybody else. Thus, a simple rule is, always read the user's own profile from the leader, and any other user's profiles from a follower. If most things in the application are potentially editable by the user, that approach won't be effective, as most things would have to be read from the leader, negating the benefit of read scaling. In that case, other criteria may be used to decide whether to read from the leader. For example, you could track the time of the last update and, for 1 minute after the last update, make all reads from the leader. You could also monitor the replication lag on followers and prevent queries on any follower that is more than 1 minute behind the leader. The client can remember the timestamp of its most recent write, then the system can ensure that the replica serving any reads for that user reflects updates at least until the timestamp. If a replica is not sufficiently up to date, either the read can be handled by another replica or the query can wait until the replica has caught up. The timestamp could be the logical timestamp, something that indicates ordering of writes, such as the log sequence number or the actual system clock, in which case clock synchronization becomes critical. See unreliable clocks on page 287. If your replicas are distributed across multiple data centers for geographical proximity to users or for availability, there is additional complexity. Any request that needs to be served by the leader must be routed to the data center that contains the leader. Another complication arises when the same user is accessing your service from multiple devices, for example a desktop, web browser and a mobile app. In this case, you may want to provide cross-device read-after-write consistency. If the user enters some information on one device and then views it on another device, they should see the information they just entered. In this case, there are some additional issues to consider. Approaches that require remembering the timestamp of the user's last update become more difficult, because the code running on one device doesn't know what updates have happened on the other device. This metadata will need to be centralized. If your replicas are distributed across different data centers, there is no guarantee that connections from different devices will be routed to the same data center. For example, if the user's desktop computer uses the home broadband connection and their mobile device uses the cellular data network, the device's network routes may be completely different. If your approach requires reading from the leader, you may first need to route requests from all of a user's devices to the same data center.